There is a force holding you at this very moment, keeping your body lying exactly where it is, gently pulling the covers over you and making the air stay around you instead of escaping into space. You don't need to think about it. You don't need to ask it to work. It simply is there, as it always has been, since the first second of your life, since the first second of the life of any human being who ever existed, since before human beings existed, since before the Earth itself existed. Gravity is perhaps the oldest and most faithful companion of everything that exists in the universe. Entire galaxies formed because of it. Stars were born and died under its influence. The ground beneath you, the planet that carries you, the sun that warms your days. All of this exists in the form. It exists because gravity, patiently, over billions of years, shaped matter into spheres and orbits and systems that spin in silence through the cosmos. And yet, there is something that physicists discovered over the last century. Something that is not exactly a problem, not exactly a crisis, but that remains like a kind of question suspended in the air. A note that doesn't resolve, a sentence that doesn't end. When they try to describe gravity using the same mathematical tools that work perfectly for all other forces of nature, something simply doesn't work. Not in a spectacular way, not with glaring contradictions, but in a quiet, persistent way, like a door that should open but doesn't, like an account that should balance but always has an inexplicable penny left over. All other forces, electromagnetism, the nuclear forces, found their place within quantum mechanics. Only gravity remains apart, working perfectly in the world of planets and stars, but refusing to be translated into the language of the very small. And there is something in this refusal that perhaps is worth observing calmly, without hurry to solve, just letting the question exist while you breathe and settle in for sleep. The first thing worth understanding is that this doesn't mean physics is broken, or that scientists are lost. Quite the opposite. The theory of gravity we have, Einstein's general relativity, works with extraordinary precision. GPS satellites depend on it to calculate your position with a margin of error of centimeters. Gravitational waves, predicted over a century ago, were finally detected and confirmed the equations with impressive accuracy. Black holes, which seemed like science fiction, were photographed and behave exactly as the mathematics predicted. In the domain of the large, the massive, the cosmic, gravity is one of the best tested and confirmed theories humanity has ever produced. The same happens with quantum mechanics in its own domain. In the world of subatomic particles, of electrons and photons and quarks, the quantum equations work with almost absurd precision. Some predictions of quantum electrodynamics have been experimentally confirmed to 10 decimal places of precision, something unparalleled in any other area of science. Computers, lasers, magnetic resonance imaging, all modern technology depends on quantum mechanics being correct, and it is repeatedly in every experiment performed. The problem arises only when you try to join the two together. When you ask, how does gravity behave at scale so small that quantum effects become important. What happens at the center of a black hole, where mass is compressed into an infinitely small point? What happened in the first instant of the Big Bang, when the entire observable universe was concentrated in a region smaller than an atom? In these extreme situations, where both gravity and quantum mechanics should be relevant, our equations stop making sense. It's not that they give wrong answers. It's worse, they give infinite answers. Absurd, mathematically inconsistent. And when equations start spitting out infinities, physicists know that something is missing, that there's a piece of the puzzle that hasn't been found yet. This piece has a name: quantum gravity, and its search has occupied some of the most brilliant minds of the last 50 years. But tonight, we don't need to solve anything. We can simply approach this territory with gentle curiosity, observing what has been discovered and what remains open. Letting the vastness of the problem be not a source of anxiety, but a kind of landscape to contemplate, while the body rests and thoughts become slower and more spaced out, like stars in a quiet region of space. Before we continue walking through this territory where physics meets its own limits, I want to say that I'm genuinely glad you're here tonight. If you're finding this exploration comforting, if you enjoy this way of thinking about reality as you relax, consider subscribing to the channel and coming back on other nights when sleep feels distant. These journeys through the quiet mysteries of the cosmos are made especially for moments like this, when you want your mind gently occupied with something vast and interesting while your body surrenders to rest. And if you know someone who might appreciate this kind of company in the late hours, share this with them. Sometimes the best gift is a peaceful way to end the day. Now, let's continue slowly, without any rush, into the strange landscape where gravity refuses to follow the rules that everything else obeys. When Isaac Newton sat beneath that perhaps mythical apple tree and began thinking about why things fall, he eventually arrived at a description that seemed complete. Every object with mass attracts every other object with mass. The attraction depends on how massive the objects are and how far apart they are. Simple, elegant, powerful enough to predict the motion of planets and the trajectories of cannonballs and the rise and fall of tides. For over 200 years, Newton's gravity was the gravity, the final word on why things fall and why the moon stays in orbit, and why you remain attached to the surface of the Earth instead of floating away into the sky. But there was always something slightly strange about Newton's description, something he himself acknowledged and never fully resolved. In his framework, gravity acts instantaneously across any distance. If the sun were to suddenly disappear, the Earth would immediately feel the absence of its gravitational pull at the exact same moment, with no delay whatsoever. This seemed to imply that gravity was somehow communicating faster than anything else in the universe. That information about where masses are located was being transmitted across the cosmos in literally zero time. Newton found this troubling. He wrote about it, admitted he had no mechanism to explain it, and essentially said that the equations work, so let's use them, and leave the deeper questions for another day. Those deeper questions waited patiently for Albert Einstein. In the early 20th century, Einstein was working on his theory of special relativity, which established that nothing can travel faster than light, that the speed of light is a cosmic speed limit that applies to everything, including information. This immediately created a conflict with Newtonian gravity. If nothing can travel faster than light, then gravity cannot act instantaneously. There must be some delay, some finite speed at which gravitational influence propagates. But Newton's equations had no room for such a delay. They assumed instantaneous action, which special relativity said was impossible. Einstein spent 10 years working on this problem. 10 years of intense thought and mathematical struggle. And what emerged was something far more radical than a simple modification of Newton's equations. What emerged was a complete reconceptualization of what gravity actually is. In Einstein's general relativity, gravity is not a force at all, not in the traditional sense. It is geometry. It is the shape of space-time itself, curved and warped by the presence of mass and energy. Imagine a stretched rubber sheet, smooth and flat. Now place a heavy ball in the center. The sheet curves, dips down around the ball. If you roll a smaller ball across the sheet, it won't travel in a straight line anymore. It will curve towards the heavy ball, not because the heavy ball is pulling it, but because the shape of the sheet guides its motion. This is roughly what Einstein proposed for gravity. Mass and energy curve the fabric of space-time, and objects moving through that curved space-time follow the paths that the geometry dictates. What we experience as gravitational attraction is actually objects following the natural contours of a curved space-time landscape. This is a beautiful idea, and it works astonishingly well. It explained the anomaly in Mercury's orbit that had puzzled astronomers for decades. It predicted that light itself would bend when passing near massive objects, a prediction confirmed during a solar eclipse in 1919 that made Einstein world famous. It predicted gravitational waves, ripples in space-time that travel at the speed of light, finally detected in 2015 by the LIGO experiment. It predicted black holes, regions where space-time curves so extremely that nothing, not even light, can escape. Every prediction of general relativity that we've been able to test has been confirmed, some with spectacular precision. So you might think the problem of gravity was solved. Einstein figured it out. We know what gravity is: curved space-time. Case closed. But the case is not closed, and the reason it's not closed has to do with that other great revolution in 20th century physics, the one that was happening at the same time Einstein was developing relativity, often in the same circles, sometimes involving the same people. Quantum mechanics was revealing that at the smallest scales, reality behaves in ways that Newton never imagined, and that even Einstein found deeply troubling. In the quantum world, particles don't have definite positions until they're measured. They exist in superpositions, simultaneously in multiple states at once. They can tunnel through barriers that classical physics says are impenetrable. They are connected by entanglement, correlations that seem to transcend space and time. And forces in the quantum description are not continuous fields, but are mediated by particles. The electromagnetic force is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force is carried by W and Z bosons. Every force we know of, except gravity, has been successfully described in quantum terms, with force-carrying particles and quantum fields, and all the mathematical machinery that makes modern particle physics so precise. The natural question, the obvious question is, why not gravity? If all other forces are quantum at their core, if everything else in the universe follows quantum rules at small enough scales, why should gravity be different? Why should space-time be smooth and continuous and classical when everything else is grainy and probabilistic and quantum? Surely gravity must also be quantum at some deep level. Surely there must be a particle, often called the graviton, that carries gravitational interactions just as the photon carries electromagnetic interactions. Surely the equations of general relativity must be an approximation, valid at large scales, but giving way to some deeper quantum description when you look closely enough. This is the problem. This is the question that has occupied physicists for decades. And the reason it remains unsolved is not lack of effort or lack of intelligence. It's that when you try to apply the standard techniques of quantum mechanics to gravity, the mathematics breaks down in ways that don't happen for any other force. The infinities that appear are not the kind that can be swept under the rug with clever mathematical tricks. They are fundamental, unavoidable, telling us that our entire approach is missing something essential. But that's a story for the next chapter. For now, you can simply rest with the image of space-time as a fabric that curves and bends, knowing that this beautiful picture, accurate as it is for planets and stars and galaxies, cannot be the final word. Something deeper lies beneath, something we don't yet understand, something that connects the geometry of the cosmos to the quantum fuzziness of the very small. And you don't need to figure it out tonight. No one has figured it out yet. You can simply let the question exist, a gentle companion as your thoughts slow down and your breathing becomes deeper and more regular. There is a procedure in quantum physics that has been remarkably successful, a way of taking a classical theory and transforming it into a quantum one. It's called quantization, and it has worked beautifully for electromagnetism and for the nuclear forces. You start with the classical equations, apply certain mathematical recipes, and out come quantum fields and particles and probabilities and all the machinery that describes the subatomic world. The process isn't always straightforward, and sometimes it requires clever tricks and insights, but fundamentally it works. Physicists have become quite skilled at it over the decades. When you try to apply this same procedure to general relativity, something goes wrong. The calculations produce infinities, which in itself is not unusual. Infinities appear all the time in quantum field theory. The key is whether those infinities can be controlled, isolated, absorbed into redefinitions of the parameters of the theory, in a process called renormalization. For quantum electrodynamics, this works. The infinities appear, but they can be systematically removed, leaving behind finite, meaningful predictions that agree with experiments to extraordinary precision. The theory is called renormalizable, which means the infinities are manageable. Gravity is not renormalizable. When you try to quantize general relativity using the standard techniques, you get infinities that cannot be absorbed, that multiply and proliferate as you try to calculate anything at higher and higher precision. Each attempt to remove one infinity introduces new ones. The mathematical structure becomes increasingly sick, increasingly meaningless. At some point you have to admit that the procedure simply isn't working, that you cannot calculate anything reliably, that the theory is telling you it doesn't make sense as a quantum theory. This is deeply strange, because general relativity is such an elegant, beautiful theory. Its equations have a geometric purity that physicists find aesthetically compelling. And yet, those same equations refuse to be quantized in the standard way. It's as if the theory is saying, I work perfectly well for describing curved space-time at large scales, but don't try to look too closely at me. Don't try to probe me at quantum scales, because I don't have answers there. One way to understand why this happens involves the nature of gravity itself. In all other quantum field theories, the fields live on a fixed background space-time. You have space and time as a stage, and the quantum fields are actors performing on that stage. The stage doesn't change, doesn't respond to what the actors do. It's just there, providing a framework within which the quantum drama unfolds. But in general relativity, space-time is not a fixed stage. Space-time is itself dynamic. It curves and stretches and responds to the matter and energy it contains. When you try to quantize gravity, you're trying to quantize the stage itself, not just the actors. You're trying to describe quantum fluctuations of space and time, quantum uncertainty in the very fabric of reality. This creates conceptual problems that don't arise in other theories. In quantum mechanics, you typically ask questions like, what is the probability of finding a particle at a certain position at a certain time? But position and time are coordinates in space-time. If space-time itself is fluctuating quantum mechanically, if the very notions of position and time become fuzzy and uncertain, then how do you even ask such questions? The framework that quantum mechanics assumes, a fixed space-time background, is exactly what general relativity says doesn't exist. There's another way to see the problem. In quantum mechanics, energy can fluctuate temporarily. You can borrow energy from the vacuum as long as you pay it back quickly enough. This is related to the uncertainty principle and leads to the prediction of virtual particles, constantly popping in and out of existence in empty space. For most forces, these virtual particles have small effects that can be calculated and measured. But gravity couples to energy, all energy, including the energy of these virtual particles. And when you add up all the contributions from all the virtual particles of all types, you get an infinite answer for the energy density of empty space. This is the cosmological constant problem, sometimes called the worst prediction in the history of physics. When you calculate what the energy density of empty space should be, according to quantum field theory, you get a number that is roughly 10 to the power of 120 times larger than what we observe. That's a 1 followed by 120 zeros. It's not a small discrepancy. It's perhaps the largest disagreement between theory and observation in all of science. And it's directly related to the incompatibility between quantum mechanics and gravity, because gravity feels all that vacuum energy and should curve space-time dramatically in response. But it doesn't. Something is cancelling almost all of that energy, leaving just a tiny remnant that we observe as the acceleration of the universe's expansion. What is doing that cancellation? No one knows. These problems might sound abstract and technical, and in many ways they are. They involve calculations that fill hundreds of pages, mathematical subtleties that take years to master. But at their core, they're pointing to something simple. Our two best theories of physics don't fit together. Quantum mechanics describes the very small with incredible accuracy. General relativity describes the very large with incredible accuracy. But when you try to use them together, in situations where both should apply, you get nonsense. The equations break. This breaking is not just a mathematical inconvenience. It points to a gap in our understanding, a place where something genuinely new is needed. And strangely, knowing that such a gap exists can be comforting. It means the universe still has secrets, that the story of physics is not finished, that there are genuine mysteries waiting to be solved. You can lie here tonight knowing that some of the deepest questions about reality remain open, that the ground beneath you and the stars above you are part of a cosmos that even our best minds don't fully understand. There's something restful in that incompleteness, something that takes the pressure off, something that says it's okay not to know everything. It's okay to rest in the presence of unsolved questions. It's okay to simply exist within a mystery that has persisted for decades and will likely persist for many more. If general relativity and quantum mechanics conflict, you might wonder, does it matter? After all, gravity is incredibly weak at small scales. The gravitational attraction between two electrons is something like 10 to the power of 42 times weaker than their electromagnetic repulsion. In any normal situation, quantum gravity effects would be so tiny as to be completely unmeasurable. Why worry about reconciling theories that operate in such different domains? Why not just use general relativity for big things and quantum mechanics for small things, and never bother trying to join them? The answer is that there are places in the universe where the two domains overlap, where you have situations that are both extremely small and extremely massive at the same time. These are the places where our current physics fails completely, where we know our equations cannot be trusted, where we need a theory of quantum gravity to say anything meaningful. And these places are not hypothetical. They exist or existed as real features of our cosmos. The most famous such a place is the singularity inside a black hole. when a massive star exhausts its nuclear fuel and collapses under its own gravity, it can form a black hole, a region where space-time is so curved that nothing can escape, not even light. At the center of this region, according to general relativity, all the mass is compressed into a point of infinite density, a singularity where the curvature of space-time becomes infinite. But infinite density means extremely high concentration of mass in an extremely small region, exactly the situation where quantum effects cannot be ignored. General relativity is predicting its own breakdown, telling us that at the heart of every black hole is a place where our equations cannot be trusted. What actually happens at a black hole singularity? We don't know. General relativity says the mass is concentrated in a point of zero size, but that doesn't make physical sense. Quantum mechanics says you can't confine something to an exact point without requiring infinite energy, which also doesn't make sense. A theory of quantum gravity would presumably resolve this conflict, would tell us what's really at the center of a black hole, whether it's something finite and describable, or something stranger that we can't currently imagine. But without such a theory, the interior of black holes remains a realm of genuine ignorance, a place where our physics simply stops working. An even more profound example is the Big Bang itself. If we run the equations of general relativity backward in time, we find that the universe was denser and hotter in the past. Keep running them backward, and you reach a point where all the matter and energy in the observable universe was concentrated in an infinitely small, infinitely dense point, another singularity. This is the Big Bang singularity, the apparent beginning of our universe, the moment when space and time themselves allegedly came into existence. But can we trust this picture? Almost certainly not. As you approach the Big Bang, you're approaching conditions where both gravity and quantum mechanics must be important. The entire observable universe, now spanning billions of light years, was once compressed into a region smaller than an atom, smaller than a proton, smaller perhaps than the Planck length, which is the scale where quantum gravitational effects should become dominant. Our equations, the equations of general relativity that predict the Big Bang singularity, cannot be trusted in this regime. They're being applied beyond their domain of validity, like trying to use Newtonian physics to describe objects moving at nearly the speed of light. A theory of quantum gravity might tell us what really happened at the earliest moments of the universe. Perhaps there was no singularity at all. Perhaps the Big Bang was actually a big bounce, where a previous contracting universe reached some minimum size and then started expanding again. Perhaps there was no definite beginning, just a quantum fluctuation out of some primordial state. Perhaps the very question of what came before the Big Bang is meaningless, like asking what's north of the North Pole. These possibilities have all been explored theoretically, but without experimental access to quantum gravitational effects, we cannot say which, if any, is correct. There's something peaceful about contemplating these extremes while lying in bed, far from any black hole, long after the Big Bang. The singularities are there, or were there, but they're abstract, distant, inaccessible. You don't need to worry about falling into a black hole tonight. You don't need to experience the conditions of the early universe. You can simply acknowledge that these extreme places exist, that our understanding has limits, that even the most successful theories we have eventually break down when pushed far enough. And there's a third place where quantum gravity matters, a place much closer to home in a sense, though equally abstract. It's the nature of space-time itself. General relativity describes space-time as a smooth, continuous fabric. But if space-time is quantum at some fundamental level, then it should have a discrete structure at very small scales, perhaps at the Planck length, which is about 10 to the minus 35 meters, roughly 100 billion times smaller than a proton. At this scale, space-time might not be smooth at all. It might be grainy, pixelated, made of discrete chunks or loops or networks of relationships. Some theoretical approaches to quantum gravity, like loop quantum gravity, explicitly predict that space comes in discrete units, that there are smallest possible lengths and volumes, that if you could somehow zoom in far enough, you would find that the smooth space-time of general relativity gives way to a discrete structure, like how a smooth-looking photograph resolves into pixels when you look closely enough. Other approaches, like string theory, have different implications, but also suggest that space-time at the smallest scales is fundamentally different from our everyday experience. We have no experimental evidence for any of this. The Planck scale is so small that we cannot probe it with any technology we can currently imagine. But theoretically, the question of what space-time is made of, whether it's continuous or discrete, whether it emerges from something more fundamental, is intimately connected to the problem of quantum gravity. Solving one would likely mean solving the other. For tonight you can simply hold these ideas loosely, not grasping for answers, but letting the questions themselves be a kind of bedtime story. Black holes and big bangs and the fabric of space-time, all these grand cosmic mysteries, reduced to the same basic puzzle. How do gravity and quantum mechanics fit together? The question floats there in the intellectual night, asking nothing of you, requiring nothing, just a companion for the mind as the body relaxes and thoughts become fewer and more diffuse. Although we don't have a complete theory of quantum gravity, physicists have not been idle. Several approaches have been developed over the decades, each with its own insights and its own problems, each representing a different guess about what the answer might look like. None of them is proven. None of them is universally accepted. But together, they represent humanity's best attempts to reach beyond the current limits of physics, to glimpse what a unified theory might look like. The most famous approach is string theory. In string theory, the fundamental constituents of reality are not point particles, but tiny vibrating strings, loops or segments of energy much smaller than any particle we can observe. Different vibrations of these strings correspond to different particles, just as different vibrations of a guitar string produce different musical notes. One of the vibration patterns corresponds to a particle with exactly the properties expected of the graviton, the hypothetical carrier of gravitational force. This was one of the early excitements of string theory. Gravity emerges naturally from the theory, without being put in by hand. String theory also has other attractive features. It seems to be mathematically consistent in ways that previous attempts at quantum gravity were not. The infinities that plague direct quantization of general relativity are absent or controlled in string theory. The theory seems to know about both gravity and quantum mechanics simultaneously, without the conflicts that appear when you try to combine them directly. For these reasons, string theory attracted enormous attention and effort over the past few decades, with thousands of papers written and entire careers devoted to its development. But string theory also has problems. It requires extra dimensions of space beyond the 3 we observe, typically 6 or 7 additional dimensions that would have to be curled up so small that we cannot detect them. It exists not as a single theory, but as a landscape of possibilities, perhaps 10 to the power of 500 different versions, each corresponding to a different way the extra dimensions could be configured. We have no way to determine which version, if any, corresponds to our universe, and most troublingly, string theory makes no unique predictions that can be tested with current or foreseeable experiments. It is a mathematically beautiful structure that might describe reality, but after decades of work, we still cannot verify whether it actually does. A different approach is loop quantum gravity. Instead of starting with strings or particles, loop quantum gravity starts directly with general relativity and tries to quantize it carefully, avoiding the mistakes that led to infinities in previous attempts. What emerges is a picture of space-time as discrete rather than continuous, made of tiny loops or networks of relationships. Space is granular at the Planck scale, composed of finite chunks called quanta of volume and quanta of area. This discreteness automatically removes certain infinities, because you can't have infinitely small distances. There's a smallest possible length built into the structure of reality. Loop quantum gravity has achieved some notable successes. It can describe the quantum state of geometry. It makes predictions about black hole entropy that match expectations, and it suggests that the Big Bang singularity might be replaced by a big bounce, where the universe contracted from a previous phase before expanding again. But loop quantum gravity also has problems. It has not yet fully incorporated matter and the other forces of nature in a consistent way. It is not clear whether general relativity emerges correctly from it at large scales, and like string theory, it makes no clear predictions that can distinguish it experimentally from other approaches. There are other approaches too. Causal set theory proposes that space-time is fundamentally a discrete set of events with causal relationships between them, from which the continuous space-time of general relativity emerges as an approximation. Asymptotic safety suggests that gravity might be consistently quantized after all, if we're willing to accept that the theory changes its behavior at high energies in a particular way. Emergent gravity proposes that space-time and gravity are not fundamental at all, but emerge from something deeper. perhaps from quantum information or entanglement. Each of these approaches captures some aspect of what a quantum theory of gravity might look like. None of them is complete. All of them might be wrong. The honest situation is that we don't know which, if any, is on the right track. We're in a period of exploration, of guessing and checking, of following mathematical clues that might lead somewhere or might be dead ends. This is how science often works at the frontiers, not with clear progress toward a known goal, but with tentative steps into unknown territory, guided more by intuition and aesthetics than by experimental data. And this uncertainty, this multiplicity of possibilities, is not something to be anxious about. It simply is the state of knowledge at this moment in history. 100 years from now, perhaps one of these approaches will be confirmed and the others forgotten. Or perhaps a completely new idea will emerge that nobody has thought of yet. Or perhaps the question will turn out to be more subtle than we currently imagine, requiring not a single answer, but a new way of thinking about what questions to ask. For tonight, you can let these possibilities coexist peacefully. String theory with its vibrating strings and extra dimensions. Loop quantum gravity with its discrete chunks of space. Causal sets and emergent gravity, and all the other ideas floating in the theoretical physics community. They're all attempts to understand something deep about reality, and they're all incomplete. You don't need to choose between them. You don't need to understand their mathematical details. You can simply appreciate that people are working on these questions, that the search continues, that the mystery of quantum gravity is being actively explored even as you lie here drifting towards sleep. There is a particular kind of comfort that comes from acknowledging the limits of knowledge, not the frustrated comfort of giving up, not the resigned comfort of accepting defeat, but a genuine peace that arises from understanding that some questions are simply open, that not knowing is itself a valid and even valuable state. We live in a culture that often prizes answers over questions, that treats knowledge as a possession to be accumulated, that feels uncomfortable with gaps and uncertainties. But the deepest scientific questions are not like trivia questions, with definite answers waiting to be looked up. They are genuine frontiers, places where even the smartest humans don't know what the truth is, where different experts disagree, where the next breakthrough could come tomorrow, or in 100 years, or never. Quantum gravity is one of these frontiers, and realizing this can shift how you relate to it. Instead of feeling anxious about the incompleteness of physics, you can feel a kind of wonder. Instead of demanding answers, you can appreciate the questions. Instead of needing everything to be wrapped up and resolved, you can rest in the openness, the uncertainty, the not yet known. This is not anti-scientific. Science thrives on questions more than answers. Every answered question opens new ones. The history of physics is not a march toward a final theory where everything is understood. It's an expanding sphere of knowledge where each increase in what we know also increases the surface of contact with what we don't know. Newton answered questions about motion and gravity, but opened questions about the nature of space and time. Einstein answered some of those questions, but opened questions about quantum gravity and the structure of space-time at small scales. Whoever eventually develops a complete theory of quantum gravity will no doubt answer some current questions while opening entirely new ones that we can't currently imagine. And meanwhile, right now, we live in a moment where this particular mystery is open. The equations don't quite work. The theories are incomplete. The smartest people disagree about how to proceed. This is exciting if you let it be. This is the universe showing us that it's more complex and subtle than we've figured out so far. That reality still has surprises in store. That the project of understanding is far from finished. There's also something personally meaningful about these limits. You are a being who exists within this mysterious cosmos, a collection of atoms arranged in a pattern complex, enough to wonder about itself, to ask questions about gravity and quantum mechanics and the nature of space and time. And those atoms are held together by forces we understand imperfectly, in a space-time whose deep structure remains unknown. You are part of the mystery, not separate from it. Your body, your brain, your consciousness, all of it exists within a universe that doesn't yet fully make sense, even to our best theories. This could be unsettling. But it can also be grounding, because it means you're not required to have everything figured out. If the universe itself contains unsolved puzzles, if reality at its deepest level involves questions that humanity hasn't answered, then your own uncertainties and confusions are not failures. They're reflections of where things actually stand. You can give yourself the same patience and acceptance that physics gives itself. The willingness to sit with open questions, to continue exploring without demanding immediate resolution, to trust that not knowing is part of the process. Tonight, as you let go of the day and prepare for sleep, you can also let go of any pressure to understand everything. The problem of quantum gravity will still be there tomorrow, unsolved and fascinating. The physicists working on it will continue their explorations, making incremental progress, following leads that might go somewhere. The universe will continue operating according to whatever its actual laws are, whether or not we've figured them out. And you can rest, genuinely rest, knowing that your place in the cosmos is secure regardless of theoretical uncertainties. That the gravity holding you to your bed works perfectly well whether or not we understand its quantum nature. That the mystery is a companion rather than a threat. And so we come to the end of this particular journey, though end is perhaps the wrong word for an exploration of questions that remain open. We have travelled from the familiar force that holds you in place through centuries of scientific discovery to the strange frontier where our best theories fail to connect. We have seen that gravity, the most familiar force, is also in some ways the most mysterious, refusing to be reconciled with quantum mechanics despite decades of effort. We have glimpsed the places where this conflict matters, the black hole singularities and Big Bang origin and fundamental structure of space-time. And we have surveyed the theoretical approaches that might someday provide answers. But more than any specific content, I hope you carry with you a feeling. The feeling that it's okay to rest within a mystery. The feeling that some questions are meant to be lived with, not immediately solved. The feeling that the universe, even with all its unsolved puzzles, is a place where you belong, where you are held, where you can let go and trust the process of simply existing. The gravity that holds you right now, in this bed, in this moment, works perfectly. It doesn't need our understanding to function. It simply is, has been, will continue to be. The planets continue their orbits. The galaxies continue their slow rotations. The cosmos continues its vast and patient existence, regardless of whether humans have figured out how to write consistent quantum equations for space-time. Reality operates. It doesn't wait for our theories to catch up. And you can operate the same way. You can exist, rest, sleep, without needing to resolve the deepest questions first. The questions will be there when you wake up. The physicists will still be working on them. The mystery of quantum gravity will remain, quietly, patiently, waiting for whoever might eventually solve it, if indeed it's solvable at all. For now, this moment is enough. This breath is enough. This gentle weight of your body against the surface beneath you. This quiet room. This gradual dissolving of thoughts into the softness of approaching sleep. The universe is vast and strange and not fully understood. And within it, here you are, a small conscious point of awareness, resting within the mystery, held by forces that work even when we don't understand them, safe even within the incompleteness of physics. Sleep well. Let the questions float away like leaves on a slow stream. Let the theories and equations and debates fade into background silence. Let yourself be held by a gravity that doesn't need your understanding to keep working. And when you wake, the cosmos will still be here, mysterious and magnificent, and you will still be part of it, one small piece of a universe that is still, even after all these centuries, learning to understand itself. Good night. Rest peacefully in the quiet space where knowing meets not knowing, where science meets its own limits, where everything that has been discovered still points toward everything that remains to be discovered. You are here now, part of it all, and that is enough, more than enough. It is quietly and without fanfare, everything.